So we are partway down the road to understanding why the square root in the middle and high school curriculum is such a problematic thing to study. In our last video, we talked about one-to-one and onto functions. And the reason that the square root is so problematic and leads to so many opportunities to misunderstand and miss solutions to quadratic equations and things like that is that the squaring function, f of x equals x squared, is not one-to-one. If you draw a horizontal line through the graph of any quadratic function generically, you're going to hit that graph in two different spots, two different inputs that give you the same output. And so it's not possible for me to define an inverse that would be single valued, right? That one output would have to go back to both of the original inputs in some way. So in this video, I want to talk a little bit about the process of constructing the inverse for a function in general, and what we can expect. What are some necessary conditions for a function to be invertible? And then I want to dig deeper into that example of f of x equals x squared from the high school curriculum to talk about not its inverse per se, but its inverses. That we'll see that because that function is 2-to-1, because it's a many-to-one function, right? It's not 1-to-1, it's 2-to-1 generically, that we can actually define more than one different inverse for it. And the key to doing that is going to be a choice that we make. And it's a choice about domains and codomains. It doesn't necessarily have to do so much with the formula that defines the rule which turns input into output, but it is our choice to define what is the universe of possible inputs that we want to consider. What is the universe of realized outputs that we get from the function? Those choices are going to be where we have the opportunity to find more than one inverse for a many-to-one function. So what does that look like? Let's get started. So first, I want to start by defining two different notions of inverse. Often when we introduce inverse functions in the high school curriculum, we speak of it as something which can undo what the original function does. The inverse of f just reverses whatever f did, right? If f is, walking forwards, then the inverse of f is walking backwards, right? If f is sitting down, f inverse is standing up. If f is putting on your socks, f inverse is taking off your socks, right? But very often that kind of language obscures that we also want the inverse to undo we also want f to undo what its inverse does. We want that relationship to be bidirectional, right? We want, putting on your socks to be the inverse of taking off your socks, in addition to vice versa, right? But we can't always expect that both of those are going to hold simultaneously. So all of that is a long wind-up to this definition, which is the definition of a left inverse of a function and a right inverse of a function. So if you give me a function f whose domain is the set x and whose codomain is the set y, then I will say that f has a left inverse, and I'm going to call it g, if g of f of x is equal to x for all x in the domain of my function. Roughly speaking, a left inverse of f is something that undoes what f does, right? So if f turns x into f of x, then g turns f of x back into x. And so a left inverse, one of the ways of keeping the terminology straight, the left inverse is something which, when I compose it with f, it gives me a function from x back to x, right? It starts in the original domain of the function f, it goes over to the codomain, and then comes back to the original domain. So that would be a left inverse. It undoes what f does. As you might suspect, a right inverse is the opposite. It's something which f undoes. Right. So it's a function, again, from the codomain of the original function to the domain of the original function, such that if I apply h first and then f, that gives me, again, an identity function, but not on the domain of the original function, on the codomain of the original function. So the right inverse of f is something which f undoes exactly. Whatever h does, f undoes. So these are the two complementary ideas of inverse. And it's very often, especially in the high school curriculum, that this distinction between left and right inverses gets blurred, because it's very often that both of them are already satisfied simultaneously. They either both fail at the same time, or they're both satisfied at the same time because of the walled garden that we construct for our students in the high school curriculum, where the examples of invertible functions that we choose automatically have both left and right inverses. And functions that have both left and right inverses, it turns out that those left and right inverses have to agree with one another and give us the unique inverse function of f. So a function that has both a left and a right inverse, we call that left and right, common left and right inverse, an inverse function of f. And it turns out we can prove that that inverse is unique in that case. So there's the definitions of left inverse, right inverse, and inverse function. Let's talk a little bit about what needs to be true about f in order that these inverses exist in the first place. So first of all, in order to have a left inverse, a function which has a left inverse, something which undoes what f does, we need f to be 1 to 1. Let's take a quick look at a proof of that. So suppose that f has a left inverse that we call g. We'll prove this by way of contradiction. So we want to conclude that f must be 1 to 1. So by way of contradiction, let's assume that f is not 1 to 1, and we'll see what happens. If f is not 1 to 1, that must mean that there are two distinct inputs in the domain, and call them x1 and x2, and they're not equal to one another. But that f blurs the distinction between the two, right? Because the outputs, f of x1 and f of x2, are the same, right? This is what it means for f not to be 1 to 1, is there must exist a pair of distinct inputs that give us the same output. But because g is a left inverse for f, by definition of left inverse, this must mean that g of f is the identity function on the domain of f. So g of f of x1 has to be x1, and g of f of x2 has to be equal to x2. After all, that's what left inverse meant in the first place. Well, what's the problem with this? The problem is x1 and x2, the outputs here on the right-hand sides of this equation, x1 and x2 are different, but f of x1 and f of x2 are equal by assumption. And that would imply that this g, this left inverse, cannot actually be a function at all. If I call x the common value of f of x1 and f of x2, then rewriting this equation here gives me that g of x is equal to x1, but g of x is also equal to x2. And the problem is that x1 and x2 are different, but the inputs to g for both of these equations is the same. So g is turning the same input x into two different outputs, x1 and x2. And therefore this g cannot be a function. And that's a contradiction, because we want our left inverses to be functions. So all of this is a long way of demonstrating that in order to have a left inverse, in order for there to exist a function that undoes what f does, f must be 1 to 1. In the same, well, in an analogous fashion, in order to have the opposite, in order for f to undo what some other function does, we need f to be an onto function. Let's take a look at why that is. In order for f to have a right inverse, we want f to be onto. Let's assume that f has a right inverse, we'll call it h, and again by way of contradiction, let's assume that the conclusion doesn't hold and that f is not an onto function. By definition of onto, that must mean that there is some element in the codomain, some y, for which we can't solve the equation f of x is equal to y, right? Some horizontal line that the graph of this function never touches, right? Some y that has no x, which corresponds to it. But because h is, by assumption, the right inverse, a right inverse of f, we must have that f of h of y is equal to y, right? For this particular y, in particular, because it's true for all y's that we could pick by definition of right inverse. But this is a contradiction, because right here, we assume that we can't solve f of x equal to y for any x, but then right here, we said we can solve f of x is equal to y by taking x equal to h of y, right? So we can't have both of these things simultaneously, right? Contrary to our findings. So we have a contradiction, so f must be onto. So in order for f to have a left inverse, it needs to be 1 to 1. In order for f to have a right inverse, it needs to be onto. Therefore, in order for f to have both a left and a right inverse at the same time, f must be both 1 to 1 and onto. So in order to have an inverse function, which is defined on the entirety of the codomain of f, f needs to have been a 1 to 1 correspondence. It needs to have been a bijective 1 to 1 and onto function. Let's pivot and talk for a few minutes about what this looks like for the real function f of x is equal to x squared. So as a function whose domain is all real numbers, and that's an important qualifier here, right? Because picking the domain of a function is a choice, right? Functions do not have only a single domain typically, right? The domain of a function is an intrinsic part of the identity, of the definition of that function in the first place. So as a function whose inputs are all real numbers, this is a 2 to 1 generically function. And so because it's not 1 to 1, it can't have a left inverse, according to what we just talked about. But it does have a right inverse. For example, the function h of y equals the square root of y. The squaring function can undo the square rooting function, right? Because if I take the square root of any non-negative real number, The result is going to be some non-negative real number, which when I square it is going to give me back the original result. The square root of y, the quantity squared, is in fact equal to y for all non-negative inputs y. So that means that the square root function is a right inverse for f of x equals x squared. But it's not the only right inverse for f of x equals x squared. Because of the sign ambiguity of taking the square, right, that's what explains why the squaring function is 2 to 1 in the first place, we could also have written h of y equals minus the square root of y. So that we're taking the square root and then reversing the sign so that we get a non-positive output instead of a non-negative one. And indeed, if I take the opposite of the square root of y and then I feed it back into my function f, right, I square it, that negative sign is going to get squared away so that f of h of y is again equal to y for all non-negative y's that I could put in. So this kind of illustrates the fact that if I have a function which is not both 1-to-1 and onto, f of x equals x squared is not 1-to-1, even though it is onto with this codomain 0 to infinity. Right? I can have a right inverse. I can't have a left inverse as a function. But in fact, I can have more than one right inverse. So we could even have told students, right, that to reverse the square operation, we could have selected the negative answer instead of the positive answer, the non-positive instead of the non-negative answer, right? Might there be other right inverses for this same function? Interesting choice. And again, that has to do with, what domain and what codomain are we choosing for my original function. So just to drive the point home further, why isn't the square root function that we saw was a right inverse for f of x equals x squared? Why isn't it a left inverse? And this is the source of the students' confusion that we looked at the top of this week's videos, is that if I take g of y equals the square root of y, if I first square a number and then I take the square root, that composition is going to give me back the original answer as long as my original input is non-negative. Right? If I put a 5 in and then I square it to get 25, then I take the square root, I get positive 5 back again. But if I start with a negative input, like negative 5, once I square it, I have lost ever the fact that the original input was negative, because now it just becomes 25, which is the same as the square of positive 5. And then the square root is no longer able to tell the difference. It's no longer able to tell which version of the square root of 25 the original came from. And since the square root function, we've agreed by convention to have non-negative outputs, it's going to give me 5 instead of the original negative 5. So it's not true that g of f of x is always equal to x. The square root does not undo what the square does, even if the square undoes what the square root does, always. So that's why the square root is not a left inverse. And again, because f of x equals x squared, if the domain is all real numbers, we can't have a left inverse at all because my function's not 1-to-1. It fails this horizontal line test at most places. So where do we go from here next? Well, we want to know how it is that we're able to surmount this problem in the high school curriculum. How do we get inverses for many-to-one functions like f of x equals x squared? And the key is that we restrict the domain. We don't look at the entirety of this graph of f of x equals x squared, because the problem is that it's a parabola with this horizontal reflection symmetry. So any point that I have on the left half plane, I also have another point in the right half plane that any horizontal line is going to hit both of them. So in order to render the squaring function invertible, we have to kind of agree that, well, let's just look at the positives instead of the non-positives. And so we restrict the domain of the square function to only non-negative inputs. And if I do that, now I get a graph that passes the horizontal line test with flying colors. And as long as I choose the codomain to be all non-negative numbers, I also have an onto function, and therefore I can come up with an inverse. And that inverse for this function with a restricted domain of only the non-negative real numbers, that function is invertible, and its inverse is what we traditionally call the square root in the high school curriculum. But that was the choice, and we didn't have to choose it that way. There might have been other ways that we could restrict the domain of this function to again render it capable of passing the horizontal line 1-to-1 test. Right? This f of x equals x squared function with this particular weird domain, this is 1-to-1 and onto. It's bijective, so it has an inverse, but that inverse might not be the same as the ordinary square root, In fact, it's probably not, because if I take the square root of any of these output values, I'm going to get a positive answer, but the original input was negative. So picking a different domain on which to restrict my many-to-one function to render it one-to-one, a different choice of that domain is going to give me a different notion of inverse function. And those are the waters that we want to swim in this week in order to understand what happens when we move up from the real case to the complex case. Stay tuned.